Here we discuss a situation where the triangle that we're trying to understand and find lengths or angles for is not a right triangle. And what comes into play here are two laws, one called the law of sines and one called the law of cosines. So the first question is, what determines a triangle? So what sort of information you have from a triangle that will pretty much pin it down? You may remember this from a former geometry experience, but there are some theorems called side, 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 angle, 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 side, angle. And just to take an example, if you're given three sides of a triangle, there's basically only one triangle up to some sort of reflections and rotations that you can make with that information. Similarly for side, angle, and angle, side. You might want to think about those things to convince yourself that it's true. There is another possible theorem that you're given two sides and an angle. And the fact is that if you're given this information, you may actually have two triangles with that information. So in the case of side, angle, the two sides and an angle where the angle is not in between the two sides. So the angle should be opposite one of the two sides, like in this picture on the right. We can see that there are two triangles with the same information, angle A and side A, and then there is, using this side of length B, or we have angle A, this A, and this B, and those are two different triangles. If, however, the angle A is greater than 90 degrees, then there's really only one solution because the other one will not make a triangle. The sum of the interior angles of a triangle is 180 degrees, so we can only have one obtuse angle in a triangle, or one angle greater than 90 degrees in a triangle. Okay, so let's look at these in turn. So here's an example of a triangle. So here are three angles and a side. So we should be able to, according to angle, side, or angle, side, angle, be able to figure out what the x and the y are. Let's talk more generally. Let's suppose we have a triangle with a side A, a side B, an angle A, and an angle B here. And what we will do is construct this height, which breaks this triangle up into two different triangles. If you compute the sine of A, you find that it's C over B, so we find an equation for C. If you compute sine B, we also find an equation for C. So we can equate these. So we solve that system of equations by substitution, if you like. And then if you divide both sides by AB and simplify, we get what's called the law of sines. What's important about this is the relationship between the A's and the B's. So A, the angle, and the side are opposites, and the angle B and the side B are opposites. I, in general, will try to make that true when I can because it helps us to be consistent. Okay, so if we have or inquire about a total of two angles and two sides and we only are missing one piece of information out of these four, then you can use this law of sines to find your missing information. So going back to our example, we have this. I'm going to try to get the law of sines displayed at the same time. So we have this information. I've highlighted the opposite pairs. So these aren't labeled with A's or B's or anything, but just think in terms of opposites. So the sine of 60 over its opposite is equal to the sine of 40 over its opposite. I wanted to use the pair 40 and 5 because those are known. So now in this equation we only have one unknown. It's a rational equation. We can multiply both sides by the common denominator and simplify. We get this. Then we divide by the factor sine of 40, and we find x is equal to 5 times the sine of 60 over sine of 40. We can put that in our calculator to estimate it at 6.74 units of length. So I'm leaving out the units of length here in all of these. The applications will have length units. Similarly, we have sine 80 over y is equal to sine 40 over 5. And so we similarly solve and we find out that y is about 7.66. By the way, it is not a good idea to use this information in the computation for y because you already have made a mistake as soon as you touch your calculator there, and you don't want that mistake to make your estimate for y worse. Okay, here's another example. Let's find theta in this triangle. So we have now two angles and two sides. We need the one angle. So we identify the pairs and write sine of 95 over 10. And that's equal to sine of theta over 5. We multiply both sides by 5, since we're just solving for sine theta here. So that's the same as sine of 95 over 2. So sine of 95 is positive, so if we divide by 2, it's still positive. So this is kind of the unit circle picture of this equation. There are two solutions. One is going to be bigger than 90 degrees, the other one's going to be less. Since we already have an obtuse angle, we have to ignore the obtuse solution to this equation. So we, in fact, even though this is a side-side angle and could potentially have more than one solution, in this case, it has just the one. So we can use the arc sine to find the acute solution, and that is 29.87 degrees approximately. Okay, what about side, side, side? Here we have no angle, so we can't use the law of sines that we just developed. So what are we going to do? This is I'm just going to state some relationships between things. So we have the three sides, there they are. And let's say an angle, and we're missing one of these pieces of information. So I want to find the relationship between A, B, C, and A. So what you can do is drop a perpendicular so that this is a perpendicular. So I've created two right triangles. Call this length D and this length E. And let's write down some equations. Using the Pythagorean theorem, we have these two pieces of information, where h is the height of the triangle. So solving that system, that is equating the right-hand sides, then we get that. So adding d squared, we get this. We have c as d plus e, so that's why I wanted d plus e here, but I can't just write that down. I have to correct for it. This is kind of like completing the square here. So I get this equation as a result. Writing d plus e is c, we get that. And I factored out a 2e out of this. The e plus d is c. So now I have an equation with a, b, c, and unfortunately e. not A. So I want to relate E and A. Well, E and A are related by the cosine. So I note that cosine of A is equal to E over B. And so E is B cosine. I substitute that back up in here for E. So I can write A squared is equal to B squared plus C squared minus 2BC cosine A. So this is the law of cosines. This is what we will use to solve a side-side-side problem. And I'm going to point out here that this looks an awful lot like the Pythagorean theorem, except there's this correction. A is playing the role of the hypotenuse, and the angle A is playing the role of the right angle. In this case, it's not a right angle. So we have this correction that's going to be generally not 0. So if, by the way, you have two sides in an angle, you may have to use a quadratic formula to find the third side, because it looks quadratic in the lengths. So you might have to use various tools. I'm just going to give one example where we're solving actually for A. So suppose we have this. We have three sides in an angle. That's exactly the ingredients we need to use the law of cosines. So what we do is we identify which of the sides is opposite the angle of interest. In this case, it's the 3. That belongs then on the side by itself. Then we kind of write down the Pythagorean theorem, except that we correct it by subtracting twice 5 times 6 times cosine of that angle theta. Now we subtract the 5 squared and 6 squared. We simplify the left-hand side. We divide by negative 2 times 5 times 6, negative, and the negative will cancel, giving you a positive. 13 over 15. So that's equal to cosine. The picture for that in terms of solving this equation is this, and only the one in the first quadrant corresponds to an angle of a triangle. So we only have the one solution that's relevant for us. That's 29.9, and we have that in degrees. Okay, you'll work on other examples in the homework.